In the intricate world of metal cutting, whether through milling, turning, drilling, or grinding, lubricants play a pivotal role as unsung heroes that safeguard both the workpiece and the cutting tool from the destructive forces of friction and excessive heat. These substances, ranging from specialized cutting oils to simpler options like wax, act as intermediaries that minimize direct metal-to-metal contact, thereby reducing the energy required for cuts, extending tool life, and preserving the integrity of the material being machined. Friction, the primary antagonist in cutting operations, generates heat through shear forces as the tool bites into the metal, potentially leading to work hardening, thermal distortion, or even tool failure if unchecked. Lubricants intervene by forming a thin film that separates surfaces, lowering the coefficient of friction from as high as 0.5 to 1.0 in dry conditions to below 0.1 with proper application, which in turn dissipates heat more effectively and prevents built-up edge on tools. For general metals like steel, cast iron, or titanium, cutting oils, formulated with extreme pressure, EP additives such as sulfur or chlorine compounds, excel at this, providing not just lubrication, but also cooling and flushing away chips to avoid rewelding. In contrast, for softer, non-ferrous metals like aluminum, which tends to gum up tools due to its ductility, paraffin-based waxes offer a clean, low-mess alternative that melts under heat to create a slippery barrier without the residue of oils. This strategic use of lubricants can reduce cutting temperatures by 30 to 50%, as evidenced by studies from the American Society for Metals, ensuring smoother finishes, higher feed rates, and reduced power consumption in shops from Mason, Ohio's manufacturing hubs to global fabrication facilities. The mechanisms by which lubricants combat friction and heat are multifaceted, beginning with their ability to lower interfacial shear stress during the cutting process. As a tool engages the metal, the lubricant seeps into the tool chip interface, preventing adhesive wear where metal particles from the workpiece bond to the tool's edge, a common issue in dry cutting that accelerates dulling. For instance, a straight mineral oil for low-speed steel cutting reduces this adhesion by promoting hydrodynamic lubrication, where the fluid's viscosity supports the load and shears easily under pressure. Heat reduction follows suit, as lubricants absorb and transfer thermal energy away from the cutting zone. Evaporative cooling from volatile components in synthetic fluids can drop temperatures by vaporizing at the heat source, while others rely on convection as they circulate. In aluminum machining, wax sticks or pastes, often applied directly, melt at around 150 to 200 degrees Fahrenheit to coat the tool and workpiece, inhibiting the aluminum's tendency to stick and generate frictional heat that could exceed 600 degrees Fahrenheit in aggressive cuts. This not only cools the process, but also minimizes built-up edges, allowing for cleaner chips and less frequent tool changes. Beyond these, advanced emulsions, water-soluble oils diluted to 5 to 10%, combine lubrication with superior cooling for high-speed operations, flushing debris while inhibiting rust on ferrous metals, a boon in humid climates like Ohio's summers, where corrosion is a perennial concern. Applying lubricants effectively requires methodical techniques tailored to the operation, tool type, and material to maximize their benefits without waste or contamination. Start by selecting the appropriate lubricant based on the metal and cut. For steel drilling, opt for a chlorine-enhanced cutting oil to handle high pressures, while aluminum milling might call for a beeswax-based stick for its non-dripping consistency. Step 1 involves preparing the setup. Clean the tool and workpiece thoroughly with a solvent like isopropyl alcohol to remove any residues that could mix with the lubricant and form abrasive sludge. Then secure the material in the vise or chuck to minimize vibration, which exacerbates heat. In Step 2, initiate a flood application for through-tool delivery if your machine supports it. Position the nozzle to direct a steady stream, about 1 to 2 gallons per minute for small jobs, at the cutting zone just before engagement, ensuring full coverage of the tool's rake face and the chip formation area. For manual tools like handheld drills, dip the bit into the oil reservoir or apply via a brush for initial wetting. Step 3 entails monitoring during the cut. Pause every 30 to 60 seconds for intermittent lubrication in prolonged operations, reapplying to refresh the film as it depletes from shear and evaporation, and adjust flow based on heat indicators like smoke or discoloration. For wax on aluminum, Step 4 shifts to direct contact. Rub the stick firmly along the tool's flutes and the workpiece edge before starting. Then reapply mid-cut by briefly withdrawing the tool to recoat, allowing the wax to melt and spread under operational heat for ongoing protection. Finally, in Step 5, post-cut cleanup is crucial. Wipe away excess with a rag soaked in the same lubricant or a mild detergent to prevent residue buildup, and inspect for even wear, repeating the cycle for subsequent passes to maintain efficacy. Cooling techniques complement lubrication by strategically managing heat buildup, with intermittent use emerging as a simple yet powerful method to prevent thermal spikes without advanced equipment. In continuous cutting, heat accumulates rapidly at the tool tip, potentially softening the tool's carbide edge or inducing microcracks in the workpiece. Intermittent application counters this by cycling the lubricant delivery. Apply for 10 to 15 seconds to flood the zone, then allow a brief dwell, 5 to 10 seconds, where the tool retracts slightly, letting ambient air or a secondary coolant mist dissipate residual warmth before re-engaging. This pulsed approach, akin to duty cycle cooling in CNC programming, reduces peak temperatures by 20 to 40% compared to steady flooding, as it permits evaporation and convection to reset the thermal gradient, particularly beneficial for dryish setups with minimal lubricant to avoid slip hazards in Ohio's variable workshop conditions. For enhanced visualization, imagine an animated heat flow diagram. Glowing red contours radiate from the tool chip interface in a dry cut, expanding chaotically like a wildfire as friction intensifies, with tool edges yellowing from 800 degrees Fahrenheit overload. Introduce intermittent lubrication, and the animation shifts to pulsing blue waves of coolant washing over the zone, contracting the red heat plume into isolated bursts that fade quickly during dwells, illustrating chips carrying away heat like conveyor belts, while the lubricant film glows green, symbolizing friction reduction and preventing the heat from propagating into the bulk material. Another sequence could depict wax on aluminum. The solid stick contacts the tool, melting into a shimmering layer that animated arrows show spreading to block heat conduction paths, with intermittent reapplication visualized as fresh wax pulses interrupting a rising thermometer graphic, cooling the process from orange to cool blue in rhythmic cycles. Advanced cooling strategies build on intermittency, such as integrating air blasts or minimum quantity lubrication, MQL, where micro droplets of oil, as little as 10 to 50 milliliters per hour, are aerosolized with compressed air to mist the cut, combining lubrication's friction lowering with air's convective cooling for eco-friendly, low-waste operations, ideal for aluminum, where excess oil can attract contaminants. In high-heat scenarios like titanium milling, pair this with through-spindle coolant delivery, pulsing at 50% duty to flood intermittently and flush titanium's gummy chips, preventing heat from exceeding 1,000 degrees Fahrenheit and causing tool galling. These techniques not only enhance lubricant performance, but also align with sustainability goals, reducing fluid consumption by up to 90% in MQL systems while maintaining the friction heat balance. Animated visuals further elucidate this. A side-view simulation of MQL shows tiny oil droplets exploding on impact like fireworks, enveloping the tool in a cooling fog that animated thermometers track, dropping from red-hot peaks during cuts to stable greens during air-only phases, contrasting with unchecked heat flows that warp the workpiece in exaggerated rippling distortions. Ultimately, mastering lubricants in cooling and metal cutting transforms potential pitfalls into predictable precision, empowering machinists to achieve flawless results with less wear, lower costs, and safer workflows across diverse applications.